All right, welcome everyone. Hello. Cool. So the plan today is to talk about mathematical induction. So this is kind of the last proof technique that we'll learn for this semester. And then you've got your kind of main bag of tricks as far as proof techniques goes. You should be good to go. So want to today kind of spend a little bit of time just the motivation behind induction and to give you some sense about how it works and some situations where it seems to apply. So the motivating example here I want to take a look at is what's called this game of Nim. And so the solutions to this are on the next couple of pages. So I'll just ask you not to look ahead to the solution, but try and think about how we could explore ways to uncover a winning strategy, if there is a winning strategy here. So the idea is you've got two piles of coins or whatever the object might be, and you've got two people, and each person is allowed to remove however many coins they want from one of the piles. And the person who takes the last coin is the winner. So for example, if we were doing this game over here, what could happen is player one could pick all of these coins, and then player two could do something really unintelligent, let's just say, and then they decide, I'm going to take this entire pile of coins, leaving one coin left. And then the first player would say, I'm going to take that last coin, and I'm the winner. So the idea is you can choose to take as many coins as you like, at least one, but you can only take coins from one pile. And then you want to think ahead to like, okay, I want to make sure that the person I'm playing against isn't therefore going to be able to take all of the remaining coins. So to kind of, I'm going to break this up into rooms just to, in pairs, just to have you guys experiment with this a little bit. And I think doing this on a whiteboard is a pretty reasonable way to do it. So for example, here's how I imagine you guys could map this out on a whiteboard. Is let's say we're choosing a game. There's two piles of two coins. So there's always going to be two piles, and there's always going to be the same number of coins in each pile. And maybe you guys could play around with having like different amounts of coins in each pile. So who wants to play with me? We'll do one round. I'm not insulted. All right, thanks, Jonathan, for volunteering. You want to be player one or player two, Jonathan? Hello, Jonathan, are you there?
Hello.
Hey, how's it going?
Sorry.
So you want to be player one or player two?
I'll be player two.
Okay, so I will go first, and I'm going to just indicate which ones I take with green. Are you good with annotating whiteboard?
Let me.
If not, you can tell me what you want to do, and I can do it for you. But I'm going to go first, and I'm going to take this one away. So now there's one pile that has the original two coins, one pile that has one coin. And so now it's your turn, Jonathan.
Okay. So I win if I just take, if there's a single coin when it's my turn?
So the winner would be the person who takes the last coin.
Okay.
So right now, you can't win because you can't take all three of those coins, right?
You win when there's a single pile, basically.
Sorry?
Oh, I was just explaining that he would win when there's a single pile, right? Since you can't take one from both piles, so as long as there's none in one pile, then he would win.
Yeah, and so, yeah, so Jonathan just took, I can see he took the one in purple, that's right. So now I can't win, right? Because I can only take a coin from one pile. And in fact, there's nothing I can do to win at this point. No matter what I do, Jonathan, that was a good move, I'm gonna lose. So whatever, I'm going to say, I'm going to take this one over here. And then I would imagine Jonathan would want to take this one over here, and player 2 wins. So that's just the gist of the game. I want to make sure it's the rules are clear what to do.
Gotcha.
Okay, congrats, Jonathan. You beat me. Good job. I won't take it personally.
Hope so.
Okay, so let me set up some rooms and just to spend about 5 minutes of playing around with this. Let's see, let me stop this. Okay, let's see. So everybody has got a partner. We have an odd number of students here, so someone is going to get stuck playing with me. Tough luck. But everybody else has. Oh, I see. Maybe I'll do a switch here, and Lindsay and I can sit this one out. Okay, and everyone's got a partner with another student in the class. Rooms are open. Yeah, feel free to play whiteboard, play a couple rounds, play around with how many coins are in each pile, see if that affects things, whatever. Okay, so we had a chance to check in with just a couple of rooms and not so much with some others, but based on what you guys were experimenting with, does anyone want to kind of summarize what might be a good strategy? Like, is there advantage for one player or the other to win? First of all, what did you guys think about that?
I thought that the advantage went to the second player.
Okay, that I didn't get a chance to chat with you guys, but that seems to line up with the rooms that Lindsay and I checked with. Does anyone have a differing opinion? And in fact, yeah, if player 2 plays the right strategy, they'll in fact be guaranteed to win every single time. So the question is, what is player 2's strategy?
You want to get it so there's one coin in each pile, and it forces player 1 to take the first coin out of one of the piles, or the last coin out of one of the piles.
Yeah, so you can kind of play backwards, and you can think, okay, if I can get to the point where player 2 has this, or I suppose this or this, right? As long as there's just stuff in one pile, then they're going to be good to go. And so the question is, how can they ensure that they're always going to be in that position? So let's say we had like 2 piles of 4 coins. And let's say I'm player 1, and I decide I'm going to take these 2 off of there. What would be a good plan for player 2 to do?
Take the same number from the opposite pile.
Yeah, and so if player 2 does the exact same thing from the other pile, it's now like we've simplified the game. So if you started playing the game with like 1 coin in each pile, in that case, it's very clear player 2 is going to win no matter what anybody does. Then you can think about, if we go to 2 coins, is there a winning strategy? If we go to 3 coins and so on, you can kind of add more coins in each pile. And what's nice about this strategy is if you've already thought about what happens in the case when there's 2 coins in each pile, right? Player 2 just seems to be employing a strategy, which is, I'm going to mimic player 1 so that the game just gets boiled down to a much simpler example, and let me try and just apply that strategy to this simpler game. So we're kind of taking more complicated cases and just saying we can do something to make these more complicated cases work the same as the more basic cases that we started with. Any other comments that you guys that came up that you want to share? Yeah, and so it seems like if player 2 does whatever player 1 does in the opposite pile, then they're going to win.
But if player 1 just takes one of the piles from either side, then they would win.
So if player 1 goes first and they take all of these coins, then player 2 is going to take all of those coins. And they would win. So the winner is the person who takes the last coin from the game. So this strategy would still apply to the situation where player 1 takes everything from one of the piles. Well, then there's still something left. There's still another pile, and player 2 is going to just mimic that strategy and take everything from the other pile. Any questions? So certainly player 1 can win if player 2 plays another strategy, but if player 2 is strategic, then they'll be guaranteed to win. So let's see how we can prove this statement in blue, right? That first of all, player 2 has a winning strategy, and secondly, what that winning strategy might be. So here's our theorem that we're going to try and prove this. And this would be hard to prove with direct proof or some other proof technique that we've talked about so far. So here we've got 2 piles, same number of coins. Second player has a winning strategy. So let's lay this out. And let's try and thinking about different cases, right? So the simplest case would be, I suppose we could have a game with 0 coins each, and player 1 would lose because there's no coins to take. So I guess another way of thinking about the winner of this game, I've been saying the winner is the person who takes the last coin from the game. You could also think about the winner is the person who gives the other person no coins to take. So that would be the case here in this trivial situation. So then we can think about, okay, what happens if we have 1 coin in each pile? And again, there's not too many possibilities to explore here, right? There's only one thing that player 1 can do. And I suppose player 2 could choose to not take any coins, but a winning strategy for them would be to take the other coin from the other pile. And we can what we need to prove is that this statement is true, that player 2 has a winning strategy for, no matter how many coins are in each pile, right? So we're thinking about 0, and then 1, and then 2, and then 3. And we could sit here for a while, right? We can try 4, and then 5, and then 6, and then 7. We want to show this for any number of coins. So like 1,000,000 coins in each pile, player 2 would still have a winning strategy. So we kind of first go about this process thinking about a couple of basic cases and try and pick up on a pattern. And that's really what mathematicians do, right? Is we try and find patterns in things. So if we have piles of 2 coins each, here's the strategy that you guys might have been discussing in your groups. Player 1 can either take 1 or both coins, and regardless of what happens, player 2 can respond. And notice here for this case, the strategy that player 2 employs is doing the same thing that player 1 did to the other pile. So if they remove 1 coin from the pile, then player 2 removes 1 coin from the pile, and they would win. If they remove both coins from the pile, player 2 removes both coins, they win. Any questions? Okay, and then we can kind of move on and think about, well, what happens in the case of 3? And then you just need to run through every single possibility, again, of what player 1 can do. So player 1 can either remove 1, they can remove 2, or they can remove all 3, right? Those are their only options. And then this is almost like a proof by cases, right? We're saying, okay, if player 1 removes 1 coin, player 2 removes 1 coin, there are 2 coins in each pile. And then it breaks down into, okay, and then we can further say, okay, well, what could they do now? They can remove 1 or they could remove both. And regardless of what they do now, right, player 2 would still have a winning strategy there. And over here, if they remove 2 coins, then there's 1 coin in each pile. That's pretty basic game. And if they remove all 3, that's about the worst strategy that you could do. Then the other person is just going to remove all 3. But in any case, if you weren't kind of sure how things were going to work, if you start thinking about it like this, maybe now you start to see that, look, what in all of these cases so far, player 2 is just mimicking what player 1 did. So let me think that that could be a winning strategy overall. So this is effective. It's just time consuming and really long, and we'll never be able to prove that this is going to be true for all values of n, no matter how many coins we put in each pile. Since, whenever we prove that we could add more coins to each pile, and there's another case that we would need to consider. So let's kind of think about how we could streamline the arguments from the previous page, where we were just like breaking down case by case, exhausting all of the possible moves that player 1 can do, and then the possible reaction that player 2 can do. So the key note here is that when we were going through this process, I went through this whole explanation over here. Again, right? I mean, like we already discussed that, look, if there are 2 coins in each pile, player 2 wins. So at this point over here, when we're trying to think about, well, what happens in the case of 3 coins in each pile, I could say, okay, if player 1 removes 1 coin, player 2 removes 1 coin, and then we're back in the case where n equals 2, which we've already proven. So we can save some time by not having to rewrite this part out, but rather kind of refer to a previous case that we've already proven. And similarly, this one over here, if they remove 1 coin from each pile, well then, excuse me, if they remove 2 coins from each pile, player 2 is going to do the same thing, and then we're back with the case where n is 1, and we've also already proven that player 2 is going to win that scenario. So basically what we're seeing here is by removing the same number of coins that player 1 removed, player 2 is able to boil this down to a smaller game, which they've already figured out how to win. So rather than have to rewrite out those arguments, we can kind of do the following for the case of 3 to write this more succinctly. So player 1 removes 1 coin, player 2 removes 1 coin. And then we can proceed as the previous case. Player 1 removes 2 coins, player 2 removes 2 coins. Then we have the case with 1 pile. And so on. So really what we're saying here is no matter what player one does, player two can do something so that this now becomes a smaller game that they've already figured out how to win. Any questions? Okay, and so then case 4 doesn't become so bad, right? Because otherwise we would have to say, well, player 1 can take 1 coin, they can take 2 coins, they could take 3 coins, they could take all 4, and you know we're adding a bunch of possibilities. So it's much easier here to just say, okay, if they remove 1 coin, see case 3, and if they remove 2 coins, see case n equals 2. If they remove 3, see n equals 1, and so on. So no matter what player 4, excuse me, what player 1 does, player 2 does the same thing. Now we've got a game for a smaller value of n that we've already proven player 2 can win. Okay, any questions? So still, what kind of remains to be seen over here, like what happens in the most general case? Like, how can we make an argument for, say, like n equals 100 or something like that? So the goal here is that, you know, if we know that player 2 has a winning strategy, right, then we could show that it's going to work for 100. Because starting with 100, no matter what player 1 does, player 2 can then put us into one of these earlier cases that they know that they can win. So kind of what's happening here is, you know, we can prove the next case as long as we know all of the previous cases were true. So let's see how we can state this more succinctly. So now we're kind of getting at the goal. We've picked up on a pattern that, okay, no matter what happens, so here we're just kind of thinking about the case for n is equal to 4. And what we can see is that player 1 can remove, you know, 1, 2, 3, or 4 coins if they want. And now, rather than have to go through each of these cases, if they remove 1, then player 2 removes 1. If they remove 2, player 2 removes 2. Now we can just more succinctly sum that up by saying, well, if player 1 removes t coins, player 2 is going to remove the same number of coins. And now we've got a case where we still have the same number of coins in each pile for a smaller value of n. So here's how we can kind of state this a lot more succinctly. So player 1 removes t coins. Player 2 removes the same number of coins. Now we've got 4 minus t coins left in each pile, which we've proven player 2 has a winning strategy. Okay, any thoughts, questions? Logic seem confusing? Make sense? Thank you for the black screen thumbs up. I can see the people that have their cameras on, can see sometimes when they're confused. It's harder when there's a black screen. So thanks for the chats coming in too. Yeah, so the question here is there an entire proof for this? Yes. So we're just focusing on the logic at this point for how this works and in situations where this might seem to apply. But yeah, we definitely need to think about how we can formally prove this. Yeah, and so there are going to be some rules that we can keep in mind when we're trying to do this process. So this process is exactly called induction. And so kind of what induction is going to allow us to do works in situations exactly like this, when more complicated situations So we can take a kind of complicated situation and show that it is no different than a more simplified version, which we've already proven. Then the induction is going to have some possibility of working out. Okay, and so yeah, so just to kind of tie this in, I think now we've got a strategy that's going to work no matter how big n is, right? If n is 5, great. Now the only thing we need to change is this over here. And we say, okay, they take t coins. T could now be as large as 5, but still player 2 can do whatever they want to make it a case of 4, and then they could make it a case of 3 in each pile and so on. So there's nothing different about what we said up here to if we just change this to any arbitrary integer over here. So the only exception to this was really what happens in case n equals 0 when we don't have any coins, and that was kind of the trivial base case that player 1 is going to lose right away because they have no coins to take, so player 2 wins. So here's one way that we can prove this a little more formally. We can say, okay, the case where we have 0 coins in each pile, that's kind of a special case because nobody can remove anything. So if there aren't any coins, player 2 wins. Let's get that cleared up. Okay, now let's think about what happens if we start to add some coins to each pile. And what we have said is that, okay, no matter what player 1 does, player 2 can do the same thing. And it becomes an earlier case that we assume that player 2 can win. So here's kind of the key thing in here, that this isn't something that we've proven, this is something that we're going to assume. So we're going to assume that if there are n coins, that player 2 has a winning strategy. And then if we assume that player 2 has a winning strategy for some values of n, then we can show that they're going to have a winning strategy for all values of n. And so the analogy here is like if you have big row of dominoes, this is often the analogy that you get. What induction is really saying is, how can we prove all of these dominoes fall over? Well, if I can show that the first domino falls over, that's kind of like the base case. And then if I can if I assume that, you know, all of these dominoes fall over, is that enough to ensure that this next domino falls over? If I can prove that that is true, that's going to be enough to prove that all dominoes fall over, right? So it's kind of like if I can show the first domino falls over, and if I can show that any domino that falls over knocks the next one over, then we know the whole trail of dominoes is going to get knocked down. Any questions? So yeah, so let's kind of think about how we could map these out, how we can write this out. So here is an example of how we can kind of prove this by induction. So here's the claim. Whoops. And below it is the proof. So just like we've been doing with contradiction, contrapositive, we should tell the reader, we're going to prove this statement and we're going to prove it using induction on what, right? We need to say what we're doing induction on. So we're going to prove this doing induction on the number of piles in each, the number of coins in each pile, n. So just going to kind of bullet out some important points here. So this is telling the reader what method you're using. Okay, then the next thing you do is prove the base case, right? So this is the first value of n, and we'll see some examples where our base case might be a couple of things, right? It might be more than one thing. Okay, so again, there might be more than one of those. We'll see some other examples of this. So you're going to prove that the statement holds for the smallest value of n. And I'll put a little s in parentheses there since it may require more than one special case. And that's what's called the base case. And so when you're writing your proofs out, yes, label this step very carefully. Tell the reader, I'm proving the base case. So you definitely want to have that label there. And then we've got the induction step. So let me kind of So what's important in this induction step, again, really important that we label that step, is we want to state the induction hypothesis. So we're going to need to assume something. It's like an if-then statement here. And so in this case, that's our induction hypothesis. We're going to assume that player 2 has a winning strategy for smaller values of n. So in other words, for values, if we have anywhere between 0 and up to, but not including integer n. that's like assuming that we have a bunch of dominoes that fall over, and then what's left to show we need to show that later dominoes are going to be knocked down, and then therefore that's going to imply that all dominoes fall down. And so if we can show that as a result of smaller numbers of dominoes knocking over later dominoes, then that's going to imply that all dominoes fall over. So kind of all this stuff is about point 4. That's the proof. So that's kind of the part that you're going to have to figure out. The first 3 steps are pretty much going to be the same in all of these cases. So you have some sort of structure to work with. I'm always going to do step 1, tell them I'm using induction. Step 2, show the base case. Step 3, let me state the induction hypothesis. And now I've got to do something with that, right? And that's the part that's going to be different in different cases. But then we get this last point over here, which is basically summarizing point 5, that we've now shown all of the things are going to fall over. So it's nice to have this included as like a conclusion to your proof. Okay, any questions? Okay, so let's give one shot here. So these are good statements when you see something like this for induction. Like if you want to show that some property holds for all integers or all natural numbers, this is a good situation for induction. So we're going to prove this formula is true. Using induction on n. So if we're going to follow this process, and again, we really want to stay very true to the outline that we have before, then what would be the next thing that we would want to do? Yeah, so we're going to go ahead and prove the base case. Thanks for the chats. And in this case, what would the base case be? What's the initial value for n here? Yeah, so n is 1 in this case. So we're dealing with natural numbers. In the previous example, we did consider the case for n is equal to 0. But here it does make sense. If n is equal to 0, then we don't have any property to consider. So this base case should very clearly just start by saying, here's what I'm going to set n equal to. And again, this comes from the fact that up here we've defined that n is coming from the set 1, 2, 3, all the way out, right? Since it's a natural number. This is a big N. So we take our base case, which is the first value that n could be, which is 1. Okay, and basically all I'm checking here is that the left side gives me the same thing as the right side. So here I've got the left side. This property is saying, what I want to show is that, this sum, which now contains only one term, is equal to n squared. So let me just say, if you want to kind of do this really systematically, let me do it that way. What I just wrote, nothing wrong with that. But we could say, okay, if n is 1, right? On the left side, we have only one thing. Yeah, there's nothing wrong with my one sentence, really succinct description, but if you want to be more thorough about it, this certainly lets the reader know exactly what you were checking to make sure that case worked out. Typically, the base case is really, plug in and into a formula and make sure you get the same thing on both sides. That's not always going to be the case, but a lot of situations that's all you need to do. Any questions so far? Okay, and then comes the induction step, and this is obviously the main part of the proof. And I'll just say there are different types of induction: weak, strong. They have all other sorts of qualifying names for induction. There is only really one process of induction. So I'm going to try and do this in a more general way that maybe will help us avoid some trouble down the line. The subtle point here is that induction works in more general situations. It's not always I need the domino right before this one to knock it over. Sometimes it might be I need the previous 3 dominoes to ensure that this one falls over. So really what induction is just saying, as long as the next case can be boiled down to a bunch of previous cases, then we're good to go. So that's what I'm going to just kind of state first. So let's assume so let me kind of just write this out in a different color as well. And so the induction hypothesis is going to be, we're going to assume that the property holds for small values of the integer. So this property here Okay, so this is just saying basically like we were in the game case that, okay, let's assume that player 2 has a winning strategy for games where the piles of coin are smaller. Then let's show that that's going to lead to a winning strategy for any pile of coins. It's really, this induction hypothesis is saying that the first K dominoes, they all fall down. Base case is saying the first domino falls down. And now we've got to do the proof. Okay, so now we want to show that this is going to hold for larger integers, for n bigger than k. So we've got like the first K dominoes falling over. Now we want to show the next ones fall over. So, you know, this structure you can kind of always sort of stick to. Up here, we've got the base case. Down here, we're going to always need to state the induction hypothesis. And this is a really nice statement to include as well, because this kind of just sets the stage to the reader, like, here's what I'm going to try and do now. Okay, so we're trying to prove this is going to hold for larger values of n. So let's consider one of them. I'll go back to my red now. So in other words, you know, and here, this is typically what will work. I'll just say that there may be some cases where we might want to pick a different value for n. But typically what you might want to do is just pick the very next value for n. So if we know that this is true for all values of n that are bigger than k, well, let's pick the next value for n, which would be the next integer bigger than k, which would be k plus 1. So if n is equal to k plus 1, let's now write out this property over here. So then what we have is 1 plus 3 plus 5 plus Okay, so I'm going to plug in k plus 1 for n. And if I can show that this property holds, in other words, that I get k squared, in this case, I mean, I get n squared back on the other side. So the goal here is we would like to show that this boils down to n squared, right? So we're hoping to show this. Because our value for n here is k plus 1, right? So again, what we're hoping to show is this property over here. So I'm going to do this for the next integer, which is k plus 1. So I'm just going to write it out like this, right? So this would be the case for k is 1. Here's when k is 2. Here's when k is 3. So I'm just writing out the previous thing in the sum that we would have right before this last term, right? So right before the k plus 1 term would come the k term. Any question about how I went from up here down to here? Okay, and now we've got exactly what was up there in green. So the reason why I did that is I just kind of pulled out the k plus 1 case, looked at the remaining sum, which is exactly like a smaller game of Nim, right? This is a smaller sum that we have assumed this property holds for. So what can I replace that expression in green with? So I got a question to clarify something, but I don't know what the something is. Which part? So that means like going from here to here. Yeah, so if we have this expression, this means 1 plus 3 plus 5 right? Each of these terms in this sequence looks like 2 times in integer minus 1. And we're increasing the integer by 1 each time. So this would be when n is equal to 1, we only have one thing. When n is equal to 2, we would say 2 times 2 minus 1, that gives me the 3. And this would be for n equals 3. This is n equals k. This is n equals k plus 1. So we were just rewriting the sum of the first k plus 1 terms as the sum of the first k terms plus the k plus 1 term. So that's where this came from over here. This is the k plus 1 term. So over here, we're just saying the sum of the first k terms plus the additional k plus 1 term. And that's a reasonable thing to do in this case because we want to break this down to like a prior case with some new stuff over here. That's right. And so I kind of asked like, okay, what can we replace this with, right? Here's exactly what we assumed. So we can use this induction assumption to say, okay, we've assumed that this works for the first k terms. So we can use this fact that, that the first k terms in this sum give me k squared. And now we still have this extra term over here. I'm just going to distribute this out. Right, so that would be 2k plus 2 minus 1. So that's where the 2k plus 1 comes from. And that expression is exactly k plus 1 squared. So basically what we just showed is, let's assume the first domino falls over. If the kth domino falls over, that proves the k plus 1 domino falls over. So therefore, they're all going to fall over, right? Because if I know that k plus 1 falls over, that knocks k plus 2 down, that knocks k plus 3 down, that knocks k plus 4 down, and so on. So that completes things. So now we're ready to say, And I don't need to kind of explain that the details of what induction is doing, right? I can assume that someone understands that as saying, okay, if the previous cases hold and that shows the next case works, then that's equivalent to showing that it's going to work for all of them. So here's kind of what the complete proof would look like. So we've got the kind of initially, here's how we're going to prove this. Here's the base case. Here's the induction step here, very clearly stated is the induction hypothesis and what I'm trying to show. And then we've got the proof. And so these typically do involve a bit of algebra, like a string of algebra. And one thing that I should mention is when you're doing like a whole succession of algebraic steps, you actually don't need to intersperse words in the midst of that. So you don't have to say, describe in words what's going on over here. But it is nice to write this out with, you know, here's what I started with, here's what I ended with, and just kind of work one string of equations down the right side. So you only have one left side. The left side isn't changing. What you're changing is the right side of the equation to show that it fits in the mold of this formula. Any questions about that? Okay, well then that's the plan. Today I just wanted to kind of get you going with what induction is in theory. And the video that you guys have to watch is probably a little bit easier than this example that we just went through. But you know, give the video a look through. It's just a bit of an introduction to induction, and you got a couple of questions on the reading quiz that are going to essentially be like, here's a problem. What would the base case be? What's the induction hypothesis in this thing? So just to identify a couple of the key points in the proof. And then we'll get busy proving things on Wednesday. So in the meantime, you know, your next homework assignment is up and it is all on induction. So all of the proofs on that assignment are induction proofs, or here's an example of an induction proof, what looks good and bad about this, those sorts of things. Okay, so that's it for today. If you guys have any questions about things, you're welcome to stick around. I just want to mention that I'm going through your exams. Things are looking fine. I'm hoping to get them done by the next time we meet, but I'll definitely get them done by this week. We'll see how busy things are tomorrow, but I'm planning to just finish up the grading tomorrow and post them for you guys on Wednesday. Okay, well, have a nice afternoon, and I will see you guys on Wednesday.